So we were discussing completion. In regarding that, in that context, I said I will show you another way of completing a metric space. So, I mean, through Cauchy sequence, we did a completion, and that is the standard way. And that is better because when you want to complete a vector space or something, you will get a vector space. And I mean, a norm will automatically, I mean, naturally will become a norm. Inner product you can extend and all that. But this is something nice, better to know this. So the proposition is the following. You have a metric space. Very not clear. Metric space. And continuous bounded functions on X. Okay. So this is contained in B of X, of course, bounded functions on X. This is closed. Of course, if we have a uniform limit of continuous function is continuous function and also bounded. Okay, it's also bounded. Uniform limit of bounded function is bounded. We have proved that. So it should be bounded. So this is a Banach space. This is contained in that is closed. So this is a Banach space. It's a not Banach space. It's complete. I'm sorry. I mean, what I said is correct, but yeah, you don't need it. Okay. So CBX is CBX is complete. Okay. Okay. Then there exists, the statement is the following. There exists an isometry P from X into, I mean, when I say right like this, it is an embedding, okay, into that CBX. There is an embedding, okay. This is a complete metric space, okay, and you can embed X into this. Once you take the closure, that will give you a completion, right? Okay. This is fine. Okay, then of course, then phi X bar is a completion. And we know completions are unique up to isometry. We have already proved that completions are unique up to isometry. So this is one of the completion. I mean, this is a up to isometry. This is the completion. Okay, you can say this is the completion. So this is the statement I want to prove. There exists. So you have CBX. I mean, this is all continuous. So I didn't say what is this. This is all continuous bounded functions. Okay, on X. Okay, on X to R or C. Okay, maybe I'll write it here. Equal to all F from X to, you can take real if you want. Let's take C such that F is continuous and bounded. Okay. We want to define our uniform norm. For that, it need to be bounded. Otherwise, we cannot define the supremum norm. So for that, it has to be bounded. So it's defined like that. So then there exists an isometry. The proof is easy. Okay. So define for X in X, define Fx at Y. Okay. I want to define a function corresponding to this X. Fx at Y is just the okay, for X in that fix some A. I fix a, this is needed to make it bounded, otherwise it's not needed. I fix a, then for X in X, define Fxy equal to dxy minus dax. That's all. Day. Okay. The statement is there exists an isometry. X can be embedded into CBX. This is all bounded continuous function. We can embed X into this. That's the statement. You complete, you taking the closure, that will be the completion. There's no complete, taking the closure will be a completion. It's another completion, that's all. Okay. So all I have to prove is, I have to prove that there exists an isometry. I have to define an isometry for this. Okay. That isometry I am defining for any X, I am defining a function. Now I have to define a function, Fxy equal to this. Okay. First, I have to verify this is bounded, this is continuous, and this is isometry. These are the three things I have to verify. So the first claim is one is f is continuous. F is continuous, it's actually uniformly continuous. Okay. I mean, we have already seen this, the same statement, same idea. This is for any A. You need this term to make it bounded. Okay. So otherwise, just dxy can be unbounded in a metric space. So that's why we are just having another dAy. Okay. So we want to talk about continuity. So for that, we have to consider this x y minus fx fxy fxz. Okay. We have to show that this is less than or equal to show uniform continuity or something. If we show this is less than or equal to d of y and z, we are done. I mean, I will show an inequality. Now this is equal to this minus this, so dxy minus day minus dxz minus daz, right? So the same triangle inequality. So you can take these two together, and triangle inequality will tell you this is less than or equal to dx is common, dyz. There is no need for this. Dyz plus again another thing is also there is a there. A will go away. Dyz. So 2 times dyz. Okay. I am define f. Huh? Here. Okay. So we have this inequality by triangle inequality. So this this is the distance between them, distance between any y z. This shows it is uniformly continuous. Is that clear? I mean, if you have any function which satisfies this condition, I mean, if you have any function f of x minus f of y is less than or equal to some c times d of xy, whatever, then this is uniformly continuous. Given a epsilon ball, you have to get a delta ball. If you take the same thing as, if there is no c, take the same epsilon equal to delta, that will work. Okay. Or using convergence also you can prove. If something xn converges to x, f of xn will converge to f of x. From that also it will follow. Okay. You take these two together, This should be plus, yeah. No, I wanted to put a bracket, I forgot. Yeah. Huh? This statement. XD is a metric space. This is all bounded continuous function. Then there is an isometry between these. Isometry means distance preserving map. Distance between phi x and phi y is same as distance between x and y. Okay. So now I have I have to define a map from x to CBX. So for any x here, I have to produce a function here. That function I am producing it as f of fx. So fx at y is this. Okay, the statement is clear. Fx at y is this. I have to define fx what is at y, and then I verified it is continuous. It's clear. From this, it's clear it's continuous, right? Okay, second. If it is not clear, check it. Okay, this should be clear. So the next thing is f is bounded. Fx is bounded. In fact, we can compute the norm itself. So mod of fxy, which is equal to dxy minus day. Y is common. This is less than or equal to dxa. Okay, so this is true for all y. So this is bounded. Something is bounded by something where there is no y here. So this is bounded. Okay. On the other hand, we can actually compute the norm of this. Okay, and it attains its supremum, attains its maximum. On the other hand, fx of x equal to fx of x is equal to, this will become 0. So mod of this is dax, which is also equal to, if you want, once again, fx of a also. Fx at a is, that is 0. This is equal to this. Okay. Yeah, these things imply, right? Wait a minute. These things imply norm of fx infinity is equal to dax, dxa or ax. What is the question? Fxy equal to dxy minus dx, that's definition, which is less than or equal to dxa. Fx is a bounded function. These things imply Fx is in, I will go to the next statement. From these two statements, we have made two statements. 1 and 2 implies Fx as a function is contained in CBX. Okay, that's what I'm making this as a function. The norm is dxa itself, because maximum is attained here at A and A are, maximum is attained, which is exactly equal to this, and is less than or equal to this, we have proved. So the supremum is less than that, and supremum is equal to that. Okay. So 1 and 2 imply it's a continuous, for each x, Fx is a continuous function and it's also a bounded function. Okay. Now we have to prove this map. Now define phi from x into CBX by phi of x equal to Fx. It's a function, that's all. Px equal to Fx. Okay. Now we define Px to be this. We have to prove it's an isometry. To prove isometry, we have to find the distance between them. Okay. Distance between them is in the norm, the infinity norm, supremum norm. We have to find the distance between them, which is distance between Fx and Fy, which should be equal to d and xy. So to find the supremum distance, we have to first find this difference, Fxy minus some other, maybe Fx prime. Yeah. Fxy minus Fx prime 1. Okay. Fixed. Yeah, A is fixed. Yeah. A is just fixed. A just depends. A is fixed. A is fixed for globally for everything. That's why I started with fix A. Okay. Okay. Now for x prime in x, to take x and x prime in x, okay, 2x and x prime. Then for Fxy minus this is equal to, you just write the definition. This is equal to dxy minus day minus dxy prime, no, x prime y minus day. Okay, day, the same ay. Okay, so they get cancelled, which is equal to dxy minus dx prime y. Okay, now this is less than or equal to dxx prime. Okay, so this difference is less than this. This is true for all y. This is less than or equal to this for all this. Okay, this implies supremum of Fxy minus Fx prime y is less than or equal to dxx prime. Okay, because it's true for all y, there is no y here, so that is true. Now we have to show that this is attained here, but Fx x minus Fx prime x, take y equal to x itself or x prime, whatever you want. Okay, take x equal to x prime. So then this becomes, this modulus is equal to, if you take x equal to, y equal to x, this is 0 and this is ax, and that will cancel with this. So this is just dx prime x. Either you take y equal to x or y equal to x prime, then the supremum is attained. What is the problem? What is the problem? F suffix, this is an element. F suffix where x makes sense. Fx is a function. Take y equal to x, I am saying. Phi is a map from x to CBX. So if you take a x, you get a function here. Okay, this has a metric here. I am define a map free from x to CBX. This is a metric space. This is a metric space. Okay. And for x here, I get a function here, fx. Distance between two function is defined through the supremum norm. Okay. And distance here is d. Okay. So to find the distance between fx and fx prime for any x and x prime, I want to show something is a, say, if you have a x, if you have a y, something is a isometry if it preserves the distance. Okay. You take any two element here, then f of that they have the same distance. Okay. So I could compute the supremum distance between fx and fx prime. I compute this. I show that by triangle inequality, this is less than or equal to this, which is trivial, of course. This statement is trivial. Because of that, you take the supremum of this over, I mean, this is supremum over y in x. Okay. And here for this is by taking y equal to x, if you want. Okay. Yeah, submetric. I mean, we are considering submetric, no? So the supremum norm is this. Supremum norm is less than this. Okay, which implies, but the supremum is attained at x and x prime also, if you want. If you substitute x prime also, supremum is attained. Okay, so supremum is attained here. So these things implies the, I mean, the norm of supremum norm of fx, I mean d fx fy, which is equal to supremum, I mean, which is equal to norm of fx minus fx prime, norm infinity. This is the supremum norm. Okay, which is the definition here. Yeah, this is the definition. Okay, which is equal to this, and that is equal to dxx prime. We have proved that is equal to dx prime. So it is an isometry. This is what it means by its isometry. That's all. It is done. Y supremum. You take x equal to y equal to x itself. Supremum is attained means at some point it should be equal. You take y equal to x in this. If you take y equal to x in this is the definition, no? Fxy is y equal to x. This becomes 0. This becomes no, y equal to x. No, y equal to x. There are two terms, no? You have to take y equal to x in this. This becomes 0. This becomes x prime x. Yeah. You will just compute. Either you take y equal to x or y equal to x prime. Both will give the same answer. Okay? No, that we have already done all those things. That we have done already. Here we are saying that I am taking the difference. You have to find the supremum of this. That is the distance between them. See, this is what I am doing. I want to talk about d fx fy, which is equal to, by definition, which is supremum of fx fy in this norm, which is equal to supremum of y in this, y in x, such that mod fx some, I mean, whatever, this is a x prime or something, x prime. Oh, sorry, I am, this is the confusion. Okay. Okay. This is the definition, so, yeah. I from x to bounded for. Yeah. It still works, right? We don't huh? What? Continuous bounded functions from x to c, that might not be complete, right? Continuous function for x to c is complete. Closed set inside bounded. Yeah, it's a closed. No, bounded functions in any set is complete. We proved in the class. Subset of bounded functions on any set. Okay, take bounded function on any set. Continuous bounded functions is also continuous because it's closed inside the absolute. Closed. I mean, it's closed inside bounded function, so it is complete. You can prove. It should be open 0, 1. Okay. Okay, take x to be closed 0, 1. Then take like that. So from close 0, 1 to r, take continuous bounded functions e to the power m. Or x to the power m. They converge to. They don't converge. No, they don't converge. Oh, it's. It is in this topology. It is. Eh? If you don't have the confusion, don't ask. It's okay. Eh? What is your confusion? That doesn't converge in uniformly. The convergence is uniform. The metric is uniform convergence. Yeah. Yeah, right. Okay. Okay. So this is an embedding. That's all. See, we already proved that if the convergence is uniform, then the limit is bounded and the limit is continuous by epsilon by 3 trick or something. I showed you in the class. But this must have been done earlier, I believe. So we have also. You want to see the proof? Okay. Okay. So this is one way of completing any metric space. So next, I want to make a definition and prove something using completeness. It's very trivial, but the statement is longer than the proof. Okay. So if we have any subset an in some metric space, any an, any sequence of subset, said to have this has a vanishing diameter. This collection has vanishing diameter. If I will define what is dn, dn goes to 0, okay, as n goes to infinity. What is dn? D of any set A is just supremum of d of xy. Okay, xy in A. You take the maximum distance, supremum distance. Okay, so that is the diameter of a set. Diameter of a set is defined as supremum between all dxy. Okay, then you have a collection of set. We say that it has vanishing diameter if it d of an goes to 0. That's all. Then the proposition is the following. If an, I mean, these are all happening in a metric space. Okay, I'm not, maybe I say it, an n equal to 1 to infinity, where an is contained in x in metric space, okay? X some metric space, and with d of an, I mean, I just write it. This is easier to write than writing vanishing diameter. With d of an goes to 0 and intersection an, n equal to 1 to infinity, is not equal to empty. Okay, then, not then. Okay, this is one statement. Suppose, what is the question? F is a function from x to some y. ANs are some collection of set whose diameter goes to 0. This definition may not be needed. It's easier to write this rather than vanishing diameter and all that. Okay, this condition is easier, so you can forget this. Okay, this is just a statement. Okay, so I just write this, which is easier for me. AN is something such that diameter goes to 0. Okay, and the intersection is, and you have a continuous function. Okay, and you have a metric here, you have another metric here. Maybe I write it x with d1 to y with d2. Okay, then f of an, this is also set, and this is d2 goes to 0. Maybe that is d1. Okay, d1 of an goes to 0, and d2 of f of an also goes to 0. It is just says that continuous image of vanishing diameter goes to 0 provided that's empty. You know written? It is continuous. Yeah, is continuous. Yeah, I said it. So continuous any function, certainly it will not work. Okay. Yeah, it does not hold. So counter example. So I mean, for closed set it will work. That is the next statement. So let us take an to be equal to this. This is a counter example. An to be this. Okay. Then intersection an equal to empty, and d of an, of course, whatever goes to 0. Okay. Clearly goes to 0. And you take f is equal to f of x equal to sine. Of course, you can't define it in 0, sine 1 by x. Sine 1 by x will take 0 to something to 0 to, I mean, that will go to n to infinity. And it will take all values, right? It will take all values for between some n pi, I mean, 2n pi to 2n plus 1 pi, 2n plus 2 pi. Okay. So f of this 0, 1 by n, that will be equal to minus 1, 1 for all n. Okay. So f of this, which does not go to 0, does not go to, I mean, diameter does not go to 0. You just write it. Diameter of f of 0, 1 by n does not go to 0. You have an to be this, its diameter goes to 0, of course. The diameter is just 1 by n, which goes to 0. Okay. And you take the continuous function sine 1 by x. Okay. And sine 1 by x, the image will be minus 1. It will take all the values, right? If 1 by x from here, if you take 1 by x, that will from n to infinity. That will certainly contain some 2n and 2n plus 2 pi, right? So it will have all the values minus 1, 1.
Assumption that it is the transition diameter and intersection being 5.
Intersection not being 5, yeah.
Not being 5. That is tail is completely
That is true. Only the tail is completely closed. Why the tail is completely closed? What do you mean by completely? All of them are closed.
after something. Every A is.
Why should be that? I mean, it is just it's non-empty. It can happen anyway, no? That is true. The tail is need not be closed. But why you have any reason?
In R, I cannot think about.
It's not thinking about. I mean, you should think about a reason to conclude that rather than not being able to think about. Yeah, if it is closed, that is the next statement. And here also it is singleton. When the diameter is it's empty or singleton. That doesn't.
Actually open. Set in after each.
No, but this is not closed, no. It has 0, so you want okay. Intersection is 0, huh? Yeah.
So this is not case of the proposal. Like, it does not satisfy.
This is counter example.
Or what happens if we remove that?
Remove that condition. Yeah, of course. Yeah. That's what someone asked, so that's why I gave counter example for intersection EAN equal to empty. Okay. Okay. Now we have to prove this. It's very easy to prove the statement. Proof. Okay. So, I mean, first the claim is, he already said the claim is intersection AN. It's not empty, so equal to some singleton x for some x in x. Okay. That should be clear because if xy are in intersection AN, I go fast because I think you know the proof. Xy are here, then dxy is less than or equal to d of AN, okay, which goes to 0. Okay. This implies d of xy equal to 0. So d of xy equal to 0 implies x equal to y. Okay. So there cannot be two elements in the intersection. If there are two elements in the intersection, then dn xy is less than d1 a1, which is assumed to be go to 0. So this is singleton. It's non-empty, so it has to contain something. It cannot have more than one element. There is only one element, which is that x. Okay, now we consider this f of x. Okay, so now let epsilon greater than 0. Okay, then f is continuous. So there exists delta such that d1 xy less than delta imply d2 of f of x, f of y. If in case I miss 1 or 2, please assume it's a corresponding metric, is less than epsilon. Okay. 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 This is for for this x. X is in that. For any take an epsilon, fix an epsilon. X is fixed already. This is this x. X is fixed. Okay, it is for this X. Okay. Now, if Y is in AN, I mean, not Y is in AN, choose N naught such that D of AN is less than delta for all N greater than or equal to M naught.
What do you mean by that X? That X is how it constructed. You have to prove
That is the claim this is equal to X for some X, and that we have proved. Yeah. That X, yeah.
That X, they have not even shown the existence of it.
We have shown the existence here. This is non-empty, so it should contain, this is claim. Okay, this is non-empty, we have proved. We have assumed. Okay, and the diameter goes to 0. Diameter goes to 0 implies there cannot be two elements. There is only one element. That element you call it X. What is assuming? We have proved. We are assuming the statement of the proposition. Here or there? D of xy is less than or equal to D of an, where because x and y are in all an, xy is in here, means xy is in all an. So this is the supremum of all those things. What is?
An converge to 0, then you can say that d1 x comma y will be greater than.
It's not great. No. There is nothing to do with greater. Greater does not come at all. This is the supremum of all those things. This is x and y is in an for all an. Okay, this is true for all n. X and y are in an for all n. Okay, so this is less than or equal to this for all n, which goes to 0. Okay, this is true for all n. Okay, I thought you know the proof, so that's why I went very fast. Okay, because you have already seen counter intersection theorem, so that's why I went very fast. Okay, it's fine. Okay, that's why I went a bit fast, and it's very easy, so I went fast. Anyway, we'll repeat this argument again in counter intersection theorem. Okay. Okay. Now I am using the continuity. For continuity, using that, I am taking an epsilon and choosing a delta. The reason I am saying is I want to prove that d of f of n, the diameter of f of n goes to 0. So I have to show that it's arbitrarily small. It's smaller than any epsilon, any arbitrary epsilon. So I choose an epsilon. For that, I get a delta here. Okay. Then I have this statement using continuity. Okay. Then I choose a n naught such that this is less than delta. Okay. Now, if y is in an, okay, dxy is less than delta, of course. X is in all an, okay. Y is in an for n greater than or equal to n naught. Okay. Then dxy is less than delta. Yeah, for all n greater than n. Okay. X is in an, then dxy is less than delta. Just the definition of the diameter. Okay, dxy is less than delta. So this implies d1 maybe, d of f of x, f of y is less than epsilon. Okay, for all y in an. And f of x is in a, and for all y in an. So you notice that f of x, f of y, both in f of an, of course. That is how anything is going to look like. So we have proved that d of f of an, which is just the supremum. The x and y are arbitrary, right? X is this, and this. Okay, x is fixed. The distance between x and y is less than this. Okay, and this is f of an, and this shows that the distance is less than epsilon. The diameter will be double that, right? Distance between any y and y prime is going to be the distance between x and y prime, sum of those two things. So notice that this is less than or equal to 2 times epsilon, which is the supremum, right? Correct? By triangle inequality. Just think about it. D of f of an is distance between any 2 points here. any 2 point here is going to look like some f of y and f of y prime. And distance between f of x and f of y is less than epsilon. Okay. Distance between another point, y is arbitrary here, x is fixed. Okay. Because of that, this is less than 2 epsilon. Should I write all the argument? Is it clear? This is okay? Okay. Okay. So this is less than the, so d of f of n is less than this. So this implies d of f of a n goes to 0. That's all. That's what we want to prove. Right? Huh? Okay. Yeah. That is the way to say something is wrong. I mean, get a counter example rather than I am not able to construct something. No, it's fine. No, that is the intuition to start with, right? No, it's absolutely right. That's how you start with. Then using that, you should construct something, and that is the way to prove it. Okay, now again another easy statement, but it's very useful. We will use it at least twice. So, which is Cantor intersection theorem. So, this is called famous Cantor's intersection theorem. You say you have seen this. Of course, this is used to prove Baer's theorem. Okay, Cantor intersection theorem. Okay, what is the statement? X is a matrix. X is complete metric space. Okay. So an contained, I mean not contained in X, contained in power set of X. You don't mind writing is or is a correction. X is collection of closed set. Okay, is a sequence of closed set. The power set I wanted to write, but you have to know into notation. An is in X. An is in X. Yeah. I initially wrote power set and then change it. Yeah. An is in X. Okay, it's a collection of sequence of closed set. Okay, and d of an goes to 0, then intersection of an equal to x for some x in X. Okay. If you have a collection sequence of closed set whose diameter goes to with vanishing diameter, whatever we define, with vanishing diameter, then the intersection is a singleton. That's what this says. Okay, proof. So we have already proved d of an goes to 0, it has to be singleton. And it is, now we have to prove that it's non-empty and I mean, that's what you have to prove. If it could be empty or singleton, yeah, it has to be decreasing. I'm sorry, I forgot. There also it is needed. Yeah, but there you don't need. Yeah, we didn't use it, right? Yeah, here it is needed. Yeah, there it is not needed. There it is not needed. Here it is needed. So it's a decreasing sequence. Yeah, you are right. I will write what it means. Decreasing sequence. That is, you have any space? Decreasing sequence of closed sets. A n plus 1 contained in an for all n. Okay. Yeah, that's why the statement has more. Oh, sorry, it's the other way. N plus 1 is contained. Yeah, it's decreasing. Yeah. What is if and only? No, it has nothing to do with X is complete. These are all statements. X is a complete metric space. I will write one by one. You have X is a complete metric space. Let X be a complete metric space. Let an contained in power set of Ax is a decreasing sequence. That is an plus 1 contains, sorry, it's again an. Okay, it's a decreasing sequence with vanishing diameter, it is d of an goes to 0. Okay, I have written everything. It's complete. An is decreasing and vanishing diameter. Then intersection of an is singleton for some x in x. Okay, this is okay. You have a decreasing sequence of set, closed set. Did I write closed set? It should, yeah, earlier I wrote, here I didn't write. Decreasing sequence of an close. Okay, I'm sorry. And last time I wrote, this time I forgot. Okay, so an is a sequence of closed. Okay. Okay. So, okay. Okay. Now let's choose any xn in an. Okay. And if m is greater than n, I mean dx for each n. Choose xn in an for each n. Each n. Okay. Then dxn xm less than or equal to whichever is greater. Okay. D of an if n is greater than m is greater than n. Okay, then xm will also be there in an. So d of an, which goes to 0. Okay. Each an has to be non-empty, of course. Otherwise, it doesn't make sense. Yeah. It's a non-empty collection of closed set which happen, right? Okay. So dxn xm goes to 0. So this implies xn is Cauchy. Okay. Since x is complete, maybe I write since x is complete, there exists x in x such that xn goes to x. But then this, after the tail sequence is in all an, okay, then xn, xk, k equal to n to infinity. This is contained in an for all n. Okay. But since an is closed, the limit x is in an for all n. Okay. So this implies x is in intersection an. Okay. And by the same argument, since d of an goes to 0, since the diameter goes to 0, intersection an n equal to 1 to infinity is singleton x, okay, which we have already shown. This argument we have already shown. Okay, that's all. Okay, we'll move to next one. We've taken a lot of time for this. Okay, let us discuss a new concept, separability. Quickly go through some examples. I'm sure you know what is countable, what is uncountable, right? That's what I've written. That sequence, the tail sequence is in an for all of them. After some time, that xk is in all of them. Tail sequence is a sequence. And that limit is also x. Since that is closed, it has to be there. Okay. Okay. So definition. So, you know, reals are uncountable, rationals are, all those things you know already, right? So, reals are uncountable. See, sequences in zeros and ones are uncountable. All those things you know. D of an goes to 0. We have already used that. We have already done. Same thing will work. Okay. Okay. Definition. A metric space X is complete if it admits a countable dense subset. If there exists, sorry, is separable. It's separable if S contained in X countable and S, I mean, S is dense. S contained in X is dense, is countable and dense. Okay? And that subset is dense. If it admits a countable dense subset, okay, that is what separability is. Okay. Then example, Q is contained in R, which is dense. So R is separable. So R is separable. Okay. And you can take continuous, I mean, finite product of set product of countable set is countable, right? If you have S1 cross S2 cross, that is countable, that you know. So Qn is contained in Rn. This is countable. So this is dense here. I mean, this is dense here because if some sequence converge here, if and only if it converges coordinate wise. I mean, with respect to any metric means we are defined 3 metric, not with respect to discrete metric or something. With respect to this metric, D1 with respect to D1, D2, D infinity, you can add DP and other things. Okay, doesn't matter. You can take any norm that will work. Okay, so Qn contained in Rn, this is also separable. Okay, what is that? Separable. I don't understand. This is the definition. What do you mean? Where is it used? Motivation is something like, see, there are, what is the notion of countable, uncountable? See, you think that you have something a length. By dividing it into half, you get something. By dividing it into half, you define something. Then by using this, by doing this, you are somehow originally in the primitive time, you might have thought that you get all the numbers, right? Possibly you get all the rational numbers are there. How do you get an irrational number? How do you get all the real numbers, which are much more than rational numbers? How do you do that? That is by, I mean, that is by mathematically doing that. So that what is the, there is no real intuition for real numbers. The actual intuition is for rational numbers, right? You know, only rational numbers, but they don't suffice. There are much more than that. Similarly, so separability is something like, so now you know real, now you know that at least everything admits a dense subset. Okay, now it is just a definition. There is no separation. In mathematics, we make definition. You shouldn't attach you shouldn't interpret anything from the meaning. Normal is something used everywhere. There's nothing normal about it. Okay, I mean, normal group, normal map, normal, there is not, so many normal is there. There is nothing about normal. You think something is normal, so you call it normal. Okay. There is nothing, it's separate means it's just, you can handle it somehow by considering this. Okay, that's all. Maybe there is something separating, I'm not sure. Let me come up with that. Okay. Okay, so with respect to this, that is okay. Now that a little bit work is needed to prove that L1 is separable. I assume these two are clear, okay for you, so I don't need to say anything more than that. This is because convergence here is basically coordinate-wise convergence, but here it's not true. Okay, so L1 is separable. I need to prove this. Okay, to prove that, let this is equal to, this is contained in let equal to all sequences. See here, my notation will work. My notation, I said, if I write it, I will erase it. X1 equal to 0 for sufficiently large n. Okay. That's the notation. For after some time, this means after some time it is 0. Okay. Otherwise, I have to write the whole thing now. Okay. All sequences. L1 of n. We didn't consider anything else. What is that? No, this is that for sequences. No, I mean, there is no other L1 we considered. We are considering only that. All summable sequence. That is a function. You can take a function. Sequences are function from n to c or something. You can take any s and then you have to define what that is through integral you can define. So L1 is separable. Then F contained in L1 are all sequences which is 0 except finitely many terms. Okay, 0 after some time, after finite something, finite number. Okay, so that's what I wrote as eventually 0. It has only finitely many non-zero entries. Okay, so first we want to show that this is separable. This is not countable. This is made up of real numbers, so it's not countable. But then sequences, I mean, let Q FQ equal to all sequences. I mean xn in Q and xn equal to 0 after some time. After some time, how do you write? So you agree with me, okay? For all n. But when I put double thing, that means for all after some time. Okay, after some time. FQ is countable and dense. FQ equal to union of Qn, n equal to 1 to infinity. Right? Where Qn sits inside L1 as, I mean, Qn, you know how Qn sits inside? Q is the rational numbers. Q sits inside L1 as something. If x1 up to xn, this will sit as x1, x2 up to xn, and then 0 everywhere. Okay. This is how Qn you identify with this. Otherwise, you have to define a map and other things. You don't need. Qn sits inside like that. This is okay. Then FQ is nothing but union of this. Okay. Countable union of countable set is countable. So FQ is countable. Okay. Now FQ is contained in F. This is dense. Okay. Any finite sequence, you can have finitely many of them. This is dense. And this is contained in L1 is dense. And this is dense. This is clear. This is clear. Now we have to prove that F in L1 is dense. That we have to prove. I mean, here, what is it? Here only the point here is this has only finitely, if you take any element here, F, this has only finitely many coordinate. So you can take finitely, in the finitely many coordinate, you can take a sequence and that converges if and only pointwise converges. Because of that, this is true. But the L1, that is not the case. So we have to prove that F in L1 is dense. Okay. So now so all we need to prove is that F contained in L1 is dense. Right? That is what we need to prove. Okay, that's what we need to prove. We need to prove this, right? So if you take a sequence xn, maybe xk, k equal to 1 to infinity, contained in L1, okay, this is equal to x bar, okay. Then you define xn bar equal to xn bar at k equal to xk if k is less than or equal to n and equal to 0 for all k greater than n. Okay. Okay, this is then xn bar is in this finite thing. Okay. Okay. Now you take xn bar minus xn, minus x bar, the L1 norm. Okay. That is equal to summation k equal to 1 to infinity xn bar at k, whatever the k value, minus x bar at k value. But the first n terms are 0. So this is equal to k equal to n to infinity mod of xk. Okay. Which goes to 0. So so you should note that we have to prove it like this. You have to note that this goes to 0 as n tends to infinity. Okay. So this implies xn bar converges to x bar in L1. Okay, so for any x bar we have produced an xn bar. So this implies f in L1 is dense. Okay. I mean, all the other things are trivial, but we have to verify this. All the other thing follows from whatever we already know. Okay. Q is dense in R, Qn is dense in Rn. So sequences in rationals with finitely many terms is dense in sequences with finitely many terms with reals or complex number if you want, then you have to approximate real and imaginary part. And final thing is to prove that this f is dense in L1. Okay. For that we need this verification, but the denseness is in L1 now. That's because the tail sequence goes to 0, which is precisely the this I have taken xn, this is the metric between xn, this is a sequence, this is a sequence. Goes to 0. So this goes to 0. That is precisely, it means xn bar converges to x in the L1. That is the definition. The distance between this and this is just this. That goes to 0. Yeah, that is okay.
xn or k is basically like the sequence we take xn.
Yeah, that's what I have defined. So this is equal to x bar k is xk. Okay, if you want x bar k, if you want to write like it. Okay. Those things should be clear. Okay. F is not countable, but it has a, if this, we know fq is countable. Fq is dense in F, is dense in this. Okay, this is countable. This is dense, then this is dense. If you have a sequence, you can approximate from something here. Given epsilon, you can do get something here. Given epsilon, you can get something here. So given 2 epsilon, you will get something here. Maybe you take epsilon by 2, epsilon by 2. Okay? These things you should work out. Okay? Otherwise, I mean, in the first course itself, these things should be clear. No? If you have something from here approximate, then by epsilon by 2 trick, you can approximate something from there. Yes? Okay. Any problem? Any problem? Huh? This part. I want to prove this. Sequences with finitely many terms is dense in L1. So I take something here. That something is xk. Okay. Something is this. X bar k equal to xk, which is just a sequence. Xn is a some sequence. Okay. Then I truncate it, find the finite thing. That is what this is. Xn k equal to xk. If k is less than this, then this is 0. Truncate it. One second, let me finish. That is equal to 0. Then I want to show that this converges, this xn bar converges to x bar. Now, for any n, xn bar at k is xk. You have a sequence this, I truncate it at the nth place up to, I mean, that gives another sequence, which is a sequence with finitely many terms. That is what this f is. Okay, so xn is in this finitely many thing. Now you compute the L1 norm, just go through the definition. And I get this, it goes to 0. Which one?
X bar.
No, he asked what is, there was a confusion. So x bar of k. I mean, that is what I used here. Okay, that is why he asked this. That's why. Okay, now it's okay. Is still a problem? Now you just try it, no? We will go through it in another example again. Okay, but similarly, this you should go through. Similarly, L2 is separable. Okay. LP. LP is separable for any p. Same thing will work. There is no difference. It is just square root is there. If you do the same thing, it will work. P less than 1 also, it's a metric space, it's not a Banach, it's not a norm space. It will work. Okay. So the next example 3 is C of 0, 1 is separable. L2 is separable. Same proof, you work it out. Same thing will work, except you have to take the square and do that. That's all. Okay. And C01 is separable. Why is it true? Huh? Yeah. Polynomials with rational coefficients, they are only countable. Okay. They are like Qn. I mean, they are like FQ. Yeah, we will prove it. Okay. Because of that. Polynomials are dense in C01. Polynomials with rational coefficient is dense here. Okay. And polynomials with rational coefficients are like this FQ, union of Qn kind of thing. I mean, as a set. Okay. So this is clear. All I have to prove now is I have to something not separable. Before that, we will see an example of separable example. So let C0 equal to all sequences xn such that xn goes to 0. Okay. This is separable. Okay. So all we need to prove, again we need to prove, I mean it's enough to prove the same f we defined like that, finitely many sequence is dense. Okay. In this topology, I mean this is with respect to, I mean this is as a subset of L infinity. Okay. With respect to this norm. Okay. Supremum norm. Any converging sequence, or you can take convergent sequence instead of this. Huh? Why do you take submetric? What else you will take? That is a metric. This is a metric. Can you find any other real metric? I mean, L1 is contained in this, all LP is contained in this, but this is not summable or something. So this is the natural metric on that. Okay. So C0 is with respect to this infinity metric. Okay. This is separable. So to prove that this is separable. Okay. To prove that this is separable, again it is enough to prove sequences with finitely many terms is dense here. Okay. So again, I do the same thing again. Okay. Take any xn, x bar equal to same f we are doing. Okay. N equal to 1 to xk, k equal to 1 to infinity. Okay. Is in C0. Okay. Then you define xn bar again, xn bar at k equal to xk if k is less than or equal to n, equal to 0 if k is greater than n. Okay. Then we want to consider the infinity xn bar minus x bar, the infinity now. Okay. The first n terms are same, so the difference will be 0. Okay. So which is just supremum of n greater than or equal to, I mean k greater than or equal to n, norm of xk, mod of xk, right? This is what is this. And that will be less than epsilon after some time. So this will go to 0. Okay. So we have produced a sequence in this finitely, I mean sequences with finitely many terms, which can approximate something here. So this is dense. Okay. So dense and C0 is separable. Okay. But the same trick will not work. If you take bounded sequence, then this will not go to 0, right? This will be some number. If you take any bounded sequence instead of sequence, this is because xn converges to 0. Okay. But xn does not converge to 0. If you take just a bounded sequence, this will be some number which will not go to 0. So this metric will not work. Okay. And that is why, but that is not a proof. But that is why, that is the reason why this L infinity is not separable. This is another example. L infinity is not separable. It's not separable. Proof. I take a subset xn such that xn is in plus or minus 1. Okay. You know this set is countable, right? Uncountable, right? Enough to prove that f sub naught is dense. No, enough to prove this is dense.
By definition, it is like that is enough to prove what?
Enough to prove separable. C naught is separable. To prove that it is enough to prove this. This is the statement. C naught is separable. I mean, if you are writing notes, it's fine. Otherwise, you listen when I am saying, right? No, C0, this is separable. We want to prove. For that, it is enough to prove this is dense. And that we are proving here. Okay, that's fine. That's all. It's good. So, the second time explaining will be make everything clear. Huh? How do you prove this? Let's go one by one. So, this is uncountable. Everybody knows, I believe. Okay. I mean, you must have seen the proof. Otherwise, go back and do that. I mean, suppose if it is, you assume that suppose if it is countable, that means you have a countable thing. Then you have a sequence with plus or minus 1. Then if you have something like this countable thing, you choose a new sequence where if this is 1 here, click a minus 1 here, that will not be here. So you can prove by contradiction, you can prove that this is it's not possible to enumerate it. Okay, enumeration means enumerating with the natural number, which is not possible. Okay. Yeah. So this is uncountable. Okay. Now, if you take any two elements here, some x bar, y bar in S sequence where the set of right. Okay. Okay. Now you take, so maybe this is equal to x bar or something. Okay. Now you take two sequence x bar, y bar. This is just sequences with plus or minus 1. This sequence with plus or minus 1 or 0, 1, whatever you want to consider. Okay. Here, then the distance between them, then the infinity distance between them, then x bar minus y bar infinity, which is just the supremum, and x bar not equal to y bar. Okay. Then the distance between them, they have to differ at least one point, and that will be just 2, right? So distance between them will be 2. Okay. So supremum will be 2. They have to differ at some point. That is why they are different. Okay. And the different thing minus 1, I mean 1 minus of minus 1, which is 2, which is 2. Okay. This is 2. Okay. Now choose open ball. Okay. B of x bar 1. Now consider this. Choose open ball. You consider this set B of x bar 1. Okay. Where x bar is in S. Okay. These are all B of x bar 1, where x bar is in S. This is number 1. You take a x bar, take a open ball of radius 1 around this. Okay. They are all disjoint collection.
Just S minus x1.
X minus?
S set minus x1.
S minus S1. I don't understand.
Like you just take S and you remove x bar from it and take it back. This will be the set.
Which one will be the set? This one. No, this is in L infinity I am taking.
This set I'm saying this is equal to
this B x bar 1 equal to
S itself.
S itself. Why?
Because every sequence if you take, we have shown that
this distance between them is 2. So if you have x bar, another y bar cannot be in there. There is nothing, it's not S bar, it will be disjoint. It can contain only one of them. It will contain only x bar from S, but from L infinity it will contain more. Okay. S is a subset of this. I am just taking this. Okay. So then if it is there is only one element here, only x bar is here. if you want, this is what you are, B of x bar 1 intersection x is just x bar, nothing else. Okay. Because the distance between any two points is 2 and you are only taking distance at 1. So it will have only one point, which is this. Okay. So this is a disjoint collection. Okay. And suppose if we have a countable dense subset, a dense means it should intersect with all open balls. And this is the uncountable collection, right? This is a disjoint uncountable collection. So suppose there exists a dense subset, something, it should contain one point from each of them. That will mean that dense subset has to be uncountable. Should I write it or is it clear? Is it okay, clear from this? Should I go through? Huh? You want me to go through? Huh? After this, what I said or this itself? So let me start with this. I want to prove L infinity is separable. I take this set. This set is just sequences with plus or minus 1. Okay. And distance between any two element here is 2. Okay. Distance is 2, number 2. That is the distance between any two elements. So I take an element in this S and take an open ball of radius 1 that can contain only x bar, nothing else. So because of that, I mean, nothing S from S, and then they are disjoint. Okay, because uncountably many balls. If we have a separable, separable, suppose if we have a countable dense set, okay, you have to have something from here. If some S naught contained in X is contained in L infinity is countable, I mean, is dense, let's not make it countable, dense, okay, then there exists some element, there exists B of x bar 1 intersection S naught is not empty, okay, for all x bar. Okay. So you will have one element from here. So you get a maybe, I mean, the notation will be like this. So there exists y x bar, okay, corresponding to any x bar in S naught. Okay, where y x bar is in this, is here. Okay, is an element here. Okay, is an element here. But then this y x bar, where x bar in S is uncountable. So you have a dense subset of this. This is contained in S naught, is uncountable. So because of that, you cannot have a countable dense subset. So it's not separable. Okay. Now it's clear. Since you are asking many explanation, I have written this. So okay. Then what else is separable? So this is an exercise. I think it's very clear. Completion of a separable. I mean, not this is easy. In the same argument. Another example is completion of separable metric space. I mean, I did not write separable metric space is separable. Okay. Completion of separable metric space is separable because if same set will work. S contained in some X contained in X bar, that is dense here, this is dense here, this is dense here. We have used that. So that because of that, this is true. Okay. Okay. Then the next one is, okay, I will make a new definition. Any subset is said to be totally bounded, or X is totally bounded, any subset is totally bounded if is totally bounded if for any arbitrary epsilon, if given epsilon, there exists some finitely many of them, xn, in A such that B of xi epsilon is union I equal to 1 to n contains that A. If you have any epsilon, then you can take n epsilon, I mean there exists n finitely many epsilon open balls which will cover this. This union will this. Cover means its union is this. N can of course vary, x1, x2, they all will vary. There exists n, there exists finitely many elements such that this is true. This is totally bounded. Okay. So then the example is any totally bounded set is separable. I mean later we will prove that a compact set is totally bounded, so that will be complete. Any compact matrix space is always complete. So any totally bounded set is separable. Okay. So what is this? Why is this true? Proof? Yeah. So choose. Okay. I am getting tired. So I leave it as an exercise. Given epsilon, given 1 by n, you get x1 up to something, some finitely many of them. Okay, a finite set such that open walls will cover that. So each 1 by n open wall will cover that, and that set will be a thing. Okay, this is exercise. Otherwise, if you can't solve it, tomorrow 3:30 we will start with this.